Hello everyone and welcome back. Last time we looked at electromagnetic induction, and what we saw was that when we had a loop of wire or moving toward a magnet or a magnet moving toward a loop of wire, we induced an EMF around the loop because of the changing flux. We're going to look at something very different today, although we're going to use some of the ideas that we looked at last time. This brings us to our next section, number 23, entitled Alternating Current Circuits. In other words, AC circuits. We have looked at DC or direct current circuits already, where we had a constant voltage source. We looked at resistors in series and in parallel, and combinations of resistors in series and parallel. But the voltage sources were always a constant voltage source. In other words, they were always applying a constant voltage, you might say a constant pressure to the current, pushing it through the circuit. For an AC circuit, we're going to use a different type of voltage source. We're going to indicate it like this, with a circle and a little sine wave. And this voltage source, rather than having a constant voltage, or rather than applying a constant voltage, is going to apply a voltage with a form that looks like a sine omega t time dependence. Omega we can think of as the angular frequency, which we know is 2 pi times the regular or ordinary frequency. So we could also write this time dependence as sine of 2 pi f times t. And all of that is in the argument of the sine, although sometimes I won't put those parentheses in there. And then there's going to be some amplitude for the voltage. We'll call it V0 or V0. So this is the form of the applied voltage. Now, what does this mean? With a DC voltage source, we basically have a constant pressure, constant voltage pushing the current through the circuit. With a sine time dependence, we're going to be pushing one way and then pushing the other way and then pushing back and pushing the other way. So we're pushing left, pushing right, pushing left, pushing right, back and forth and back and forth. So we might expect then, and this is exactly what's going to happen, is that the current is going to slosh back and forth. When we're pushing one way, the current might go that way. When we're pushing the other way, the current might go that way. Maybe a little out of phase, in phase, something like that. We'll see in just a few minutes. But that's the idea. We're going to assume a particular orientation. When the sine is positive, for say the first half of the wave, we'll assume that means the left side of the power supply is the high side, the right side is the low side. When the sign is negative, then these will be reversed. So what's happening is initially we're going to be pushing current out this way, pulling it in this way, and then on the other half of the sine wave we'll be pushing the current out that way, pulling it in this way, and then back and forth this way, and then this way, this way, this way. What we're going to do today is look at 3 very simple AC circuits that are going to have the very same shape, you might say. We're going to put 3 different things in here connected across the power supply. We'll start with a resistor, then we'll look at a capacitor, and then we'll look at a third circuit element that we haven't talked about before, but that's what's going to draw on some of the ideas that we talked about last time with the electromagnetic induction. The circuit element is actually called an inductor, and we'll see what that means in just a minute. But let's get started. We're going to stick a resistor in here and see what happens. So here we go. Here's our circuit. We've got our AC voltage source applying a voltage of V0 sine omega t, and we're going to connect it with a resistor. Let's assume the resistor has a resistance R. Again, we're going to assume that when sine is positive, that means the left side is positive and the right side is negative. And then on the other hand, when sine is negative, this side will be negative and this will be positive. But we'll typically just draw it this way, and keep in mind, whenever we have a negative voltage, everything is the other way around. For a positive side, high side of the voltage here, that's going to push the current out this way and give us a current in that direction. So the current comes up, goes through the resistor. Remember, current goes uphill or downhill. Does water flow uphill or downhill? Water flows downhill. Current flows downhill. That means if the current is going this way, it's going from the high side of the resistor to the low side through the resistor. So this is the high side of the resistor, that's the low side of the resistor. Okay, very good. Now let's apply the loop rule. Let's start our loop, Kirchhoff's loop rule. Let's start our loop over here and go around the loop, and we'll go around in a clockwise direction. Starting here, we come across here, we jump across the power supply. What's the change in the voltage? Well, that's the voltage of the power supply, V0 sine omega t. Continue along. We are going to assume, like we usually do, that the resistance of the wires is negligible compared to anything else in the circuit, so there's no voltage change as we move along a resistor. It's a bit of an approximation, but it's pretty good one if we remember the resistances of wires that we found before. We continue up here, jump across the resistor. We're going from the high side to the low side, so that's going to be a voltage decrease. What is the voltage across a resistor? Remember Ohm's law, V equals Ri, very important. V equals Ri, so we have a voltage drop of Ri here minus IR, Ri. That then brings us back to where we started, equals 0. Let's bring the IR to the other side. We have IR equals, or Ri, V0 sine omega t, divide both sides by R, we have I equals V0 over R sine omega t. What we notice is the current, I, has a time dependence, sine omega t, and just let me mention right now, it's the same time dependence as the voltage. The current and the voltage are in phase with each other. What does that mean? That means when the voltage is up, positive, and up, the current is positive and up. When the voltage is down, negative, the current is down. So they are together. As the voltage goes up, the current goes up. As the voltage goes down, the current goes down. They are in phase with each other. They're not doing something different like that. They're doing exactly the same thing. And the amplitude of the current, the term that multiplies that sign dependence, is V0 over R. We can write that as the amplitude of the current, I0, where the amplitude is V0 over R. So what does the current look like? Well, it looks just like a sine wave, just like the voltage does. The current goes up and down and up and down with an amplitude. In other words, it comes up to a maximum value. What's the maximum value of the current? Well, the maximum value that the sine can have is positive 1. So the maximum current we'll have is positive I0. It comes up to a maximum value of I0. And what's the minimum value? What's the minimum value that sine can have? Negative 1. Down to negative I0. So the current is oscillating from a value of positive I0, negative I0, positive I0, negative I0. And it's oscillating between those sinusoidally. Very, very good. Now let's just keep in mind a couple things. We've got a couple relationships that I want us to keep in mind. First of all, the relationship between the voltage amplitude and the current amplitude is, right down here, multiplied by R again, we have V0 equals R I0. Ohm's law, looks like Ohm's law. But let's keep in mind, this is something a little bit different. This is not just V equals Ri that we would get from a DC circuit. What are these quantities? V0 is the voltage amplitude, I0 is the current amplitude, and R is the resistance of the resistor. It has exactly the same form as Ohm's law, but these are not time-dependent quantities. These are amplitudes of time-dependent quantities. We can divide both sides by the square root of 2 and write each amplitude as the RMS value. So we could write this in exactly the same form, but using the RMS values rather than the amplitudes. So we've got VRMS equals RIMS also. Very, very good. That's as far as we need to go for the resistor. Let's take a look at a similar circuit, but now let's use a capacitor. What happens then? Here we have a very similar circuit, but I've replaced the resistor with a capacitor. And let's assume our capacitor has a capacitance C. Again, we're going to apply a voltage source of V0 sine omega t. Same polarity, positive on the left when sine is positive. That is again going to give us a current in the clockwise direction for a positive voltage. Again, let's apply the loop rule. What do we have? Well, let's start over here. And we jump across the power supply. What's the voltage change? The voltage of the power supply, V0 sine omega t. Come along, jump across the capacitor. Now, wait a second, let's think about this for a second. We've got a current going up this way, and that's going to charge up the capacitor with a positive charge on the left side, a negative charge on the right side. What's the voltage across a capacitor? Remember, what's the relationship between the charge, the capacitance, and the voltage? Q equals CV. So we have Q equals CV. The voltage across the capacitor will then be Q over C. We're going from the positive to the negative side, so that's going to be a voltage decrease. So we have minus Q over C. That's the voltage drop across the capacitor, and then back to where we started, equals 0. Bring the Q over C to the other side and multiply by C, and what do we get? We get Q equals C V0 sine omega t. It looks like the charge on the capacitor, Q, has a sine time dependence with an amplitude of C V0. So we can write this as Q0 sine omega t, where Q0 is the amplitude of the charge, where Q0 is then C V0. So we can graph what the charge looks like. The charge on the capacitor is going to be time dependent, and it's going to look like a sine wave, just like the voltage source. So when the voltage is high, the charge on the capacitor is high. When the voltage is low, the charge on the capacitor is low. And the charge is going to be going up and down and up and down. In other words, it's sloshing back and forth, charging up one side, charging up the other, discharging, charging up the other side. So the charge on the capacitor is sloshing back and forth from one plate to another. Okay, very, very good. One problem is that typically we're not as concerned with the charge on the capacitor as we are with the current in the circuit. With the resistor, we actually found out what the current in the circuit was doing. Here, we're finding what the charge on the capacitor is doing. What we would like to know is what's the current doing. Often, knowing what the current is doing is what we really would like to find out. How are we going to find that? Well, let's think about that for a second. The current, let's remember, is what is charging up the capacitor. So this has got some charge, positive Q on one side, negative Q on the other side. The current is what's charging up the capacitor. As the current flows up, it's depositing charge on the capacitor plate, and that's what is changing Q. How much is Q changing? Well, let's imagine Q changes some amount, delta Q, in some time, delta T. The amount that the charge on the capacitor increases, delta Q over delta T, that must be how much charge is flowing up through the wire in some time, delta T. But that is exactly how we define the current. So the current is related to the charge on the capacitor by delta Q over delta T. How much Q is changing per time. If I is positive, Q will be increasing. If I is negative, in other words going the other way, Q will be decreasing. Well, how can we find out what does I look like? Well, what is delta Q over delta T? If we have a Q versus T graph, what is delta Q over delta T? Maybe if you think about this in terms of X and Y, what is delta Y over delta X? If you have a graph, what is delta Y over delta X? It's the slope of the graph. It's the slope of the line on your XY graph. So delta Q over delta T is actually the slope of our graph here. At any particular point, whatever the slope is, that's going to be our current. Well, let's take a look at that. Let's take a look at what is the slope of our Q versus T graph, and that will tell us what the current is.